Welcome to Science Store online classes.
Don't forget to like our video and subscribe our YouTube channel for all the updates.
Welcome to all of you once again to the physics classes. Dear students, we are going to talk about magnetism and matter, some of the formulas or the synopsis part of the magnetism and matter. So as of now we have discussed about moving charges and magnetism. We have considered most of the cases of charge. A charge is moving and it creates a magnetic field, and magnetic field we have written. Okay, like that. Whatever may be the concept is related to the charge. Whatever may be the thing, a charge is moving, a current, like that it is. But whereas in the case of magnetism and matter, it is a magnetism. Just a bar magnet we are going to take, and what is the physics behind that, what are the formulas, what are the properties, what are the mathematical tools that we are using to understand that magnetism, that we are going to study. So we must have a perspective here when we studying this is only about a magnet. Only a magnet is kept, bar magnet, and what are the other properties. Several things we are there to study now. Okay, so first what we have studied, a solenoid. So as per the thing only we are going to, as per regular class we have studied, same thing we can discuss, and same way the extended manner, extended formulas we can discuss here. So at the first we were discussing about a bar magnet. Bar magnet how we can form, that is nothing but by a solenoid, right? A solenoid which forms as a bar magnet. So solenoid is nothing but a rod or hollow rod, on that a wire is called, okay, we know that a coiled wire behaves as if like a bar magnet, right? One pole is north, one pole is south, isn't it? One pole is north and one pole is south, like that it is. Now, okay, so now here also the number of magnets are together formed. Actually it is a small magnet, no? One coil is nothing but a small magnet, one coil is nothing but a small magnet, isn't it? Like that it is. Okay, so north, south, north, south, north, south, north, south, north, north, south, north, like that poles. So magnetic dipoles it formed. So that became because of the small magnets. Now the dipole moment is nothing but, magnetic moment is nothing but I into A. Magnetic moment is nothing but I into A. Okay, so that is what the charge is moving. So when it consider a bar magnet, when you consider a bar magnet, for the bar magnet we will be having, that is one pole is north, one pole is south. Okay, so this is nothing but a geometrical length, isn't it? Some geometrical length is there, but actually there is a magnetic length. Okay, geometric length is there, magnetic length is there. Magnetic length is different, geometric length is different. Actually those poles are found a little bit inside to that of the ends of a magnet. Okay, that becomes a magnetic length, and this becomes magnetic charges. Okay, so generally what we will say, see, clockwise means that is inside, no? Clockwise means it behaves as if like a north pole. Anti-clockwise means it is outside the magnetic field. Okay, that behaves as if like a north pole, isn't it? That we have written, isn't it, in this way. Okay, so here also for the poles some strength is there, that is called pole strength. Small letter we are going to write on it as pole strength. Okay, M is nothing but a pole strength we are going to write down. So magnetic moment for a bar magnet how we can give? Magnetic moment for the bar magnet, that is by using capital letter we are going to write down, that is nothing but magnetic moment into the length of the magnet, the length of the magnet. Okay, so here also we can write down. So generally we are going to write down it as negative. Okay, negative magnetic charge. This becomes a positive pole strength. That is to denote south and north pole. South is always negative coming inside, no, the magnetic field, it is going out like this. So magnetic charges we can call it. Okay, we are going to call it. Okay, so but whatever, this is a magnetic. Okay, plus minus let it be. Okay, just you should know, that's all. So this is pole strength into 2L, that becomes a magnetic length. But again there is a ratio for magnetic length and geometric length, for magnetic length and geometric length. So magnetic length divided by geometric length is nothing but 5 by 6 or nearly equal to 0.84 in the ratio, that is magnetic length to that of the geometric length, always it will be in this way. Okay, so now magnet is there. Okay, the axis from north to south pole which is passing, that is called magnetic axis. Now I have a bar magnet in this way. Okay, so north pole to south pole one axis is passes, that is magnetic axis. Now vertical plane passing through the magnetic axis becomes magnetic meridian. Now take a sheet of paper and put it exactly in between, at the middle of that, and pass it like this. No, that becomes magnetic meridian which exactly passes through it. Okay, so what is the direction of that magnetic moment in the magnet, bar magnet? Always that magnetic moment is from south to, okay, always magnetic moment from south to north here. Okay, or always magnetic moment direction will be south to north. So what is the SI unit and what is the SI unit for the magnetic moment? We can write down, see, I into A, isn't it? So that is nothing but ampere meter square, isn't it? Oh, okay, so this is pi r square. Okay, area I into A. So pole strength, that is nothing but M is nothing but ampere meter. We are going to write down ampere meter, pole strength. Okay, so the SI unit. Okay, so dimension formula is M0, L1 is there, T0, ampere 1 is there, like that. Okay, but for IR square, how you are going to write down? IA. For the magnetic moment, how you are going to write down? That is nothing but you have I means current, A is there, A means L square, A means area, that is L square. The dimension formula, M is 0, L, T is 0, like this you are going to get. Okay, this is the dimension formula they are going to ask you. For all the quantities, dimension formula is must and necessary. Now everything we are going to talk about magnetic moment. Everything we are going to talk about magnetic moment for the different orientation and for the different things of magnet. Okay, so just now what we have studied only about magnetic moment and magnetic pole strength. One is pole strength, another one is magnetic moment. Now I have given a magnet in this way, pole strength is M. I will cut exactly in this way. What happened? 2L will be same, no, but pole strength becomes half of that. Exactly in the middle I am going to cut, means area you are going to reduce. Area going to reduce. So what happens? Pole strength becomes half. But whereas the same magnet I am going to cut exactly in the vertical plane, here it is horizontal, the vertical means that area remains same, no, so that pole strength remains same, but 2L will be divided into 2. 2L means what? That is the length. Why it is 2L? Don't ask such questions, okay, because it is for convenient we have taken. See, dipole moment 2A, it is 2L, okay, like that it is 2L we have taken, okay, and like that in this way it is. Now length is half, length is halved. Now what I will tell is, that is nothing but, if generally if I talk this, I am going to cut it into n parts horizontally, then what is the magnetic moment? So what happens horizontally if I cut means that pole strength is divided into n times. No. So magnetic moment is 2L into m, right? So what is the changed magnetic moment for this? The changed magnetic moment is 2L is nothing but same, no, that length into, that is into m is divided by n. The magnetic moment of each part will be this much, okay. Sorry, here it is small letter m, so m by n, but 2Lm is capital M, so m becomes n, will be the magnetic moment of the each part. Now what I am going to do here, also I am going to do the equal parts into n times vertically. Then what happens to the, but earlier it was the magnetic moment was 2Lm into n. Now n parts it is divided means m is equal to what is divided? Length is divided into m times, but pole strength remains n times, pole strength remains constant, but 2Lm into m is nothing but m, and the pole strength of the each part is nothing but m dash, which is equal to m by n, like that we can write down. Now we are going to talk about some of the orientations of the bar magnet if we orient in a different way, okay. What are the magnetic moments are going to happen? What are the changes in the magnetic moment we are going to get? That we are going to find out, okay. For the different orientation we are going to talk. Now a magnet is there which is having length 2L, okay. So this is the magnet, north and south pole. What I will do, I will cut it in equally 3 parts and I will arrange it in this way, okay. This becomes north, south, north, south, north, south. Magnetic moment is from the south to north, and south to north, in this way, no. What is the net magnetic moment it is going to happen? That is nothing but the distance between them, distance. See, for m by 3 means all the magnetic moment of the individual. So now if you are listening this means just one by one cases I am going to write down, no, that you just write down, okay. And what I am going to explain, so every heading I am not going to write down, but I am going to tell you, okay. Then equal magnet, a magnet is cut into 3 parts and arranged in the manner as shown in the figure, okay, like that. So magnetic moment is changes, no, magnetic moment is exactly divided into m by 3, no. Now what is the net magnetic moment? That is the length between them, okay, length between them into, okay, the magnetic moment, m into pole strength will be same, that is 2L is divided into 3 times, no, it is 3 out of that, out of 3 1, no, into m. So total net change in magnetic moment of this arrangement you are going to get as m divided by 3, like this you are going to get, okay. This is one of the arrangement, okay. Now we have say for example a bar magnet is bent to an arc of circle subtending an angle theta. Okay, this is north and this is south. Okay, like this. This is theta means exactly I am going to write down this length I want. Okay, to find out the magnetic moment of this arrangement. Okay, so I will write down this as y, I will write down this as y. This is r, no? So this becomes theta by 2. This becomes theta by 2. Now what is the magnetic moment? The change in magnetic moment is 2y. 2y into pole strength. Now pole strength will be remain same. We are not going to affect that pole strength, but distance between them is changed. What is that 2y? We have to find out. What is that 2y? We have to find out. Now if I say arc is nothing but, so like this angle is there, no? Y it is 90 degree and this is theta by 2. This is r. So I can write down sin theta by 2 is equal to opposite by hypotenuse. Opposite by hypotenuse, that is nothing but y is equal to r sin theta by 2. 2y means 2r sin theta by 2. No, so I can substitute here, that is nothing but 2r sin theta by 2 into m. But what is r? What is r? R is nothing but we have a ratio, isn't it? See, this formula is there. If it is delta S means it is R means theta means L is equal to R theta. Trigonometry formula is there, no? L is equal to R theta. L is equal to R into theta. No. So here also this total length is 2L. 2L is equal to R into theta, isn't it? R is equal to 2L by R, isn't it? Now we have what we want? R is equal to 2L by theta. So I can get, that is nothing but 2R sin theta by 2 m divided by R is nothing but, okay, L, which is nothing but you have to apply for R, that is nothing but 2L divided by theta. So we are going to get 4L, or okay, that is nothing but 2L into m is nothing but magnetic moment, original magnetic moment, and sin theta by 2 divided by theta, that is m dash. Okay, so this is the general formula you should know. This is the general formula we should know. Okay. So this is the case if we apply this thing for all other things. Okay. See, now it is like a bow, isn't it? So you are tied like this and you are going to pull it in this way, no? If you pull it means it will bends. How you can pull it? It becomes a circle also, or it can become straight, and it will be in this way also. Okay, and if you cut it means it becomes straight, right? That kind of situation. If suppose I am going to stretch it in such a way that theta is equal to become pi, means I am going to allow it, okay, some angle theta, no, then what is going to happen? Theta is equal to pi. Okay, substitute pi there. So m dash will be equal to 2m sin pi by 2 means how much? So sin pi by 2 means how much? So pi by 2, 90, that is 1, and divided by theta means pi. So for that you are going to get 2m by pi we are going to get, isn't it? For 2m by pi we are going to get in that way. If suppose any other angles, say for example it is 2 pi, I have made a circle. No, I have made a circle in such a way that pi is equal to 2 pi, theta is equal to 2 pi. 2 pi means sin pi and 2 pi. So if theta is equal to 2 pi, the magnetic moment is equal to 0. For a closed, okay, for a closed form, there is no magnetic moment. There is no magnetic moment. It may be a circle, but the arrangement must be north south north south north south. It may be a circle, maybe of square, or it may be a triangle, north south north south north south. In this way it is there, means magnetic moment for the closed one it becomes 0. Okay, this is the thing. So if suppose I will do a arrangement in this way, if suppose I will consider for the right angle, okay, that bow is there, no, it is not stretched in this way, it is stretched and brought here. Okay, so like that means this becomes pi by 2. So theta is equal to pi by 2 means if you apply here means m dash, which is equal to 2m sin pi by 2 means it is pi by 4, that is 1 by root 2 and pi by 2, isn't it? So it becomes 4m by root 2. So this is the thing, 4m by root 2 we can get by, okay, this is the thing, we are 4m divided by into 2 we are going to get, this is the thing. Okay, four m by root 2 pi is there. Okay, yeah, that is the thing, that is what we are going to get. Now suppose I have already a magnet which is bent like this and whose magnetic moment is the reverse case. Earlier I had a magnet, I was bending it to the circle, and I have different cases I have written. Now already I have a magnet which is bent like this and whose magnetic moment is m. Now what I am going to what I am going to do, I am going to straighten it to the straight bar. So what is the magnetic moment I am going to get? The bent one is made it as a straight. Okay, then the newly formed magnetic moment I can give the old magnetic moment divided by theta into 2 sin theta by 2 sin theta by 2, like this I am going to get. This is what we are going to get. Now we will write down some of the combinations for the magnetic moment. Okay, if it is written north to south, south to north, in that way combination is the same combinations. Okay, so say for example, north south, I am going to give always we will write down like this. Okay, from south to north, isn't it, the magnetic moment, south to north. Here one magnet is there whose magnetic moment also south to north. The same poles are kept over the one another, the angle is theta between them. So south to north, so I can write down like this, no, two vectors in this way. Then having magnetic momentum, what is the net magnetic moment? The net magnetic moment is nothing but square root of m square plus 2 m. So now I am going to write down m1 m2 means m1 square m2 square to m1 m2 cos theta it becomes. That is what earlier in the first standard first PUC you have studied. This is the concept you have studied, basic mathematics of the vectors. Now if I suppose opposite way I have connected, okay, the same one, okay, south north, but I have kept the north pole on south. So this becomes in this way. The magnetic south to north becomes in this way. So I can write down a diagram of this way. Okay. So what is the angle between two vectors? This was theta, and this it is pi minus theta. This it is pi minus theta. If suppose this is m1, this is m2, the net magnetic moment will be equal to m1 square plus m2 square plus 2 m1 m2 cos pi minus theta. Cos pi minus theta means it is cos pi minus theta means there is nothing but again cos theta we are going to get. So you can write down m dash which is equal to m1 square plus m2 square plus 2 m1 m2 cos theta. You can write down, isn't it, cos theta? You can write down, this is the cos pi 180 minus theta, that value you write down and you are going to get the answer here. Okay, so this is what the thing. So this is some of the combinations. Okay, this is some of the combinations of the magnet. Now, so for other arrangements we are going to talk about the magnets. If you in a different arrangement, if you do the arrangement of the magnets, then what is the total magnetic moment, that we are going to see. Okay, if magnet is arranged in this way, where south pole and the north pole and north pole and north pole is connected like this, okay, which is having a magnetic moment m1 and m2. What is the net magnetic moment? It becomes net magnetic moment is C. In the opposite manner, isn't it? Theta is 180 degree. If suppose m1 is greater than m2, what we have to do? m1 minus m2 we have to do. If suppose north pole is connected to the south pole of the another magnet, and this magnetic moment in this way, this magnetic moment in this way, in the same direction means here there must be repelling opposite forces. This will be in this way, this will be in the opposite way, but here it is both are in the same. So magnetic moment will be m1 plus m2. Now what if north south and north south you are going to keep, and what if south north and south, okay, in a different way it is, okay. So north south you are going to keep. On parallel basis you are going, this was in a series basis, on the parallel one over the another you are going to keep it, but same pole on the another and different poles on the another. If a different poles means see, north to south to north, south to north, in this way, again that will becomes a difference, that will becomes a different, and again here south to north, since theta is equal to 0, okay, and you are going to get the magnetic, single magnet it becomes, right. So, magnetic moment is 2 times it becomes. If M1 and M2 means that you have to add M1 plus M2. If it was M and M means definitely it is 2 times M you are going to get, and this is what the arrangement, or this is what the things we are going to get when 2 of the magnets you are going to combine in this form. Okay, these are the sum of this. So, everything what we have studied here, that is the arrangement of the magnets. So, arrangement of the magnets you will do in certain manner, so that you are going to get the magnetic moment. Simple, only one thing we have studied as of now, that is magnetic moment, pole strength and the directions, and for the different arrangements of the magnet, how the magnetic moment can be calculated, how the so there are several other things also we have to study. Okay. So, this is about some of the magnetic moment arrangements. Okay. So, now we will see certain kind of arrangements of a bar magnet which are kept in right angles to each other. See, it may be arranged in this manner, this north, south, north, south. It may be arranged in this manner, north, south, north, south. That is nothing but what? From the 90 degree to each other. Now, it may be arranged in this manner, that is south, north, south, north. Here all the magnetic moment becomes square root of m1 square plus m2 square, m1 square plus m2 square, because cos theta is 90, cos 90 is 0, so that m1 square plus m2 square it becomes in that formula. Now, if I give a example for that, we have arranged in the manner of this. This is m by 2, this is m by 2, this is north, south, north, south, south to north like this, south to north like this. The magnetic moment will be in this way, we can say. So, this is L length, L length. We do not want L length, we want the magnetic moment of the whole arrangement. What is the formula? That is magnetic moment is equal to m1 square plus m2 square. Okay, m1 square plus m2 square. We are not talking about the length of this ear angle. Do not confuse with the earlier bow shaped one. Okay, that is circle. Here it is different arrangement of the combination of the magnet we are talking. So, m1 is how much? M by 2. m2 is how much? M by 2. Generally, total magnetic moment I can write down, no? M by 2 for this is in x axis, that is in negative x axis, plus m by 2 is in y axis, that is positive y axis, positive y axis. So, total it becomes m is equal to how much? M by 2 whole square plus m by 2 whole square, square root of that, root 2 m by 2. Root 2 I can write down here, 1 root 2 cancels, so that you are going to get m by root 2. This is what the magnetic moment m dash for this kind of magnets. Now, what I will do is, I will take the magnets of equal magnetic moment and I will form a closed polygon. So, I will write down just by writing the lines, not the magnet. So, it is a magnet, is a magnet, is a magnet. I will form a triangle, I will form a rectangle. Now, it is of equal magnetic moment, but it is a closed loop, north, south, north, south, north, south, north, south, in this way. What is the magnetic moment? magnetic moment is 0. Magnetic moment is 0. For the closed loop, the magnetic moment is 0. If suppose any one of this magnet, you are going to reverse north south, north south, north south. Now south north if you do means the magnetic moment of this arrangement is becomes 2m. Magnetic moment of this arrangement is becomes 2m. Now there is arrangement in such a way that for the equilateral triangle, one is m, another one is 2m, another one is 3m. The net magnetic moment you have to find out, and it is from like this, north south, north south, north south, it is arranged. Now it is south to north, south to north, south to north. Okay. Closed loop means this is 1m plus 1m, no, this is 1m plus 1m plus 1m. 1m is get cancelled because one magnetic moment, that is closed loop 0, remaining it is 2m and remaining it is 2m. Remaining it is 1m, in that remaining it is 2m, no. So I can write down in this way, one is m is remaining, another one is 2m here. So this is 60 degree means the total arrangement I can write down in this way, no. This is 2m, this is m. So now can you have mind that, see, this I can write down m plus m, this I can write down 2m plus m, m 0, because that one is made 0. Now 0 next m plus 0 m plus 0 m, m 0 m plus m plus m, m plus m plus m if I write down means closed loop like this. Second one is not there, so 1m is there, 2m is there, I can write down in this way, no. So that I can write down. If it is 60 degree means, okay, if it is 60 degree means how much this angle, okay, that is nothing but total it is 180, so 120 degree. So now the magnetic moment becomes, which is equal to m square plus 2m whole square plus 2 into m into 2m 2m into cos 120 degree, right, cos 120 degree, and that you are going to get it as root 3m, root 3m you are going to get, cos 120, that value you must know for all the problems. And this is what enough for today's class. Okay, that is what the combinations of magnets, all those things you have studied. Here only all the cases we are going to study. Okay, they are talking about magnetism and matter and some of the formulation, only the magnetic moment and magnetic pole strength and the orientation of that we have discussed. And we were discussing about if this kind of magnet is there, that is m or 2m and 3m. Okay, so we are going to take 1m from this and 2m from this, so that we got the expression for that totally, right. And if suppose one more orientation is there in nothing but it is in this way, that is, if suppose, okay, this is m, this is 2m, this is 3m and this is 4m. Okay, so equal and opposite cancels up, so m 2m is remaining, 2m cancels, you can get here 2m, okay, and 2m you can get, okay, like this. So what is the angle between them? Angle between them is 90 degree. So this is capital M, capital M. So the net magnetic moment we can write down square root of 2m whole square plus 2m whole square Okay, a square plus b square, isn't it? 2 into 2m into 2m into cos 90 degree. So you are going to get square root of 2m square plus square root of 2m square, 2 times square root of 2m square, so that you are going to get root 2 times, okay, 2m you are going to get, root 2 times 2m you are going to get, that's how 2 root 2m, in a nice way we can write down, that is nothing but 2 root 2m. This is the thing. So no need to worry about this to buy out all those things, so just know, you should know. So one problem you may get, okay, there are some more formulas you have to study once again. Now there is arrangement like this. See, single magnet I am going to give you in this way. Now what I am going to do, half of that I will make it as a circle, and after that half of that I will arrange it in this way. Okay, next what happens, half of that I will arrange in this way, and half of the magnet I am going to arrange in this way, such a way that I am going to get south, north, south and north pole. Actually the magnetic moment of this becomes m1 and magnetic moment this becomes m2, right, because arc means it is changed, right. Now what is the total magnetic moment of this m dash, which is equal to m1 plus m2. Okay, so actually the magnetic moment becomes half, right, m by 2, isn't it? But what is the magnetic moment if it is made to arc? That is nothing but we are going to get 2m by pi, isn't it? 2m by pi plus m by 2. This one is m by 2, right? But 2m means not actually m, this is 2m by 2 by pi, no. So you are going to get 2m by 2 pi or pi m by pi plus m by 2. So common denominator if you do means 2 pi, you are going to get 2m plus pi m. So m is the common term, you are going to take pi e plus 2 or 2 plus pi, this is m dash, okay, in this way. Now suppose the same thing you are going to do the 2 plus pi, 2 plus pi into m, this is 2, okay. Now suppose the next case is there, that I am going to give like this, here north south, okay, south north in this way, okay. Now what is the magnetic moment of this? What is the magnetic moment of this? Because they are perpendicular, right? So when two magnetic moments are perpendicular, what we have to do? m1 square plus m2 square, square root of that, true? Earlier we have done that. Now again m dash I am going to write down square root of m1 square plus m2 square. But m1 is nothing but how much? m1 is nothing but like this, no, m by 2, like this, 2 times m by 2 and pi, no, that is 2 times m by 2, that is nothing but m by pi I am going to get whole square plus m by 2 whole square I am going to get, m by pi whole square I am going to get, m by 2 pi whole square I am going to get. Then do it, right, do it, whatever the equation you are going to get, tell me. So you do that along yourself, so that square means m square by pi square, and 4 pi square I am going to get, that 4 pi square I am going to take it out, so that I am going to get 2 pi, square root of remaining is, that is nothing but 2m square plus pi square or 4m square by, that is 4 pi square we had got, so that we took it out and we are going to get here 4m square plus pi m square, in that way we are going to get. So m you can take it out, So m square is common, m square, so 4 plus pi I am going to get, 4 plus pi. This is the equation, 4 plus pi. Okay, so this is the equation we have got, 4 plus pi square, because pi square goes there. This is the equation goes. So this kind of numerical sums, this kind of problems we may get. Now we are going to talk about in the basis of electric charges. See, we have spoke about electric charge or electric charge, you know, but here also dipole means it like that only, right? So it is like that only, isn't it? A magnetic charge. South I am going to write down, north I am going to write down. South means minus m, north means plus some m I can write down, isn't it? Because the magnetic field is coming inside, the electric field is coming inside. So this becomes a magnetic charge. This becomes a magnetic charge, right? This becomes a magnetic charge. Okay. Now that become a magnetic charge. Now magnetic charge is there means there is a force, there is a field, there is a potential. Okay, so magnetic force between these magnetic charges we can write down. Magnetic force we can write down. So F is equal to mu naught divided by 4 pi into m1 m2 divided by r square, the distance between them. In that way we can write down. So if m1 and m2 are same, m1 and m2 are same, that will be repulsion, and m1 and m2 are different, that will be attraction, because north and north pole will be repulsed. Same means repulsion. Okay. Now the next case what we are going to write down, that is nothing but magnetic field. How you are going to write down the electric field? Similar way you are going to write down the magnetic field. So there it was 1 by 4 pi epsilon naught, here it is mu by 4 pi, mu naught by 4 pi, and magnetic field we have written, electric field we have written q by r square, isn't it? Here it is m by r square. M is nothing but the pole strength we are going to write down. And similarly the potential we have written, isn't it? The potential, the electric potential we have written, that is 1 by 4 pi epsilon naught. Okay, q by r we have written, no? So here mu by 4 pi is equal divided by m by r we have written, m by r we have written. That is the case, that is the thing. If the magnetic charge is kept in a magnetic field, okay, if a magnetic charge that is kept in a magnetic field, that is in an external magnetic field, what happens? It will experience as a force. It will be going to experience as a force. So what is that force experienced? Force So magnetic charge is a hypothetical concept. Actually there is no like magnetic charge, but for a pole, because of the pole strength, what is the magnetic field? What is the force experienced? That is nothing but force which is equal to m into b. That is nothing but force is equal to m into d, m into b. Okay. Now what is the magnetic field in different cases that we can write down? Magnetic field. So electric field you have written, right? So now I am having a magnet, a bar magnet. On the axis what is the field? On the equatorial line what is the field? That we have to find out. So north pole is there, south pole is there. On the axis P. So this is L and this is L. Okay. So this point I am going to consider it as D. At point P, because of north pole, the magnetic field is in this way. Okay. At point P, because of south, magnetic field is towards this, right? Now, what is the expression? How we can find out the magnetic field? On the axial line, we have written the magnetic field on the axial, we have written the electric field on the axial line. Similarly, we are going to write down the magnetic field here. So, magnetic field will be, which is equal to mu naught divided by 4 pi into, that is 2 into m into d, that is nothing but 2 into m into d divided by d square minus l square to the power square. Now, if d is very much greater than l, what we are going to write down? B is equal to mu naught divided by 4 pi and m by d cube, 2m by d cube you are going to write down. Okay. So, that is the thing. No, direction is same as that of the magnetic moment. What is the magnetic moment? Magnetic moment in this way, south to north. Here the effect because of the north is maximum, means it is maximum. Effect because of the south is less. So, the total net field is will be same as that of the magnetic moment here. Okay, at this case same as that of the magnetic moment. So, here also you can write down, no, because of this like this only, because of north also like this only. So, wherever on the axis the magnetic field will be same as that of the magnetic moment direction. Okay, like this. These are the approximation consideration. But if I consider the magnetic dipole north and south and a point on the equatorial line, so that we will call on the equatorial plane, or that we can say broadside on position. Okay, broadside on position, or else it is a perpendicular bisector, isn't it? Perpendicular bisector, in any names it can be called. Now, the south means it is towards, north means it is in this way, magnetic field. Okay, equatorial plane. Now, what is the magnetic field for the equatorial plane? It is 2 times, it is 1 time, no? So, which is equal to mu naught divided by 4 pi into m d divided by d square minus l square to the power square. Now, next you can write down, that is d is very much greater than l, means d is very much greater than l means b is equal to mu naught divided by 4 pi, and m by d cube. That is what we have written now for the case of electric charges and electric field. Also we have written the same way, So, a little bit variations here we have got and we are writing. But what is the direction? See, the direction of the magnetic field on the equatorial plane, the magnetic moment is on south to north, but here it is, the direction is opposite to the magnetic moment. Now, next, okay, we have studied magnetic field on the equatorial line as well as on the axial line. So, what about the potential? Potential also we have studied in the case of electric field, no? Potential on the axis of a dipole, right? So, means that is nothing but unit positive charge you are going to bring. Similarly, here if you consider means the magnetic potential at a point P on the axial line, you can give as, that is nothing but potential which is equal to mu naught divided by 4 pi into m divided by d square minus l square. Okay, d square minus l square. In the denominator, square is not there. Earlier it was square was there, this much. Okay. Now again I am going to make the consideration in such a way that d is very much greater than l, means v which is equal to mu naught divided by 4 pi m divided by l square I can get, Okay, so here we are going to get d square, okay, earlier d square we can get where, okay. So this is the case for the potential. Now again for the equatorial plane means when you are going to bring this to the equatorial plane, is there any work is done? Because both attraction and repulsion takes place, right? Attraction and repulsion takes place. Mean the equatorial plane, there is no work is done. So potential on the equatorial plane is 0. Potential on the equatorial plane will be 0. Okay. So that is the thing. That is about some of the concept that is related to the electric field. We are going to write down in the case of magnetic field. Already we studied about the potential and when the bar magnet is kept in external magnetic field, or what are the cases or the field at any point we have studied. Now bar magnet is kept in external magnetic field means what happens? So suppose it is in this way, this is south, this is north, its own magnetic field will be in this direction, right? So external magnetic field means you are going to keep in this way, means what happens? This is going to attract, the force on this edge is m into b, the force on this edge is m into b. That is one side, this is another side. So what do you mean by the net force? Net force acting on the magnet is 0. Net force acting on the magnet is 0. Now the torque is also 0, isn't it? But if suppose you are going to make it an angle to the field, now the magnet we have kept, this is north and this is south. For the external magnetic field, which makes an angle theta, this is north, this is south. North means it repels, m into b will be in this way. South means it is repels, m into b will be in that way. Now what is the equation we are going to get? That is nothing but torque which is equal to r cross f. What is this perpendicular distance? This is 2l, right? So it is 2l sin theta we are going to get. That is nothing but 2l sin theta we are going to get. So what is the total this torque? That is nothing but r cross f. If we write down means r is nothing but 2l sin theta and force is nothing but m into b. So you are going to get 2l into m into b sin theta. So 2l into m is nothing but how much? M. B sin theta. So you are going to get m cross b, and which is equal to torque. Torque will be always perpendicular to magnetic field and magnetic moment. See, the magnetic field in this way, magnetic moment is in north to south in this direction, means perpendicular, it must be perpendicular towards you, torque. So it is rotating. It is a right hand screw rule, isn't it? Right hand screw law. In this way the magnetic field is going, means in the opposite way it is going to rotate. In that way it is, okay, whatever. This cross product is there, means this m, b and tau are perpendicular to each other, So what is the thing we are going to get? We are going to get in such a way that is the torque. We only are interested to know the expression of torque. Okay. Now suppose I will do some work to rotate that against that magnetic field, means I am going to do some work. Work is nothing but against the torque we have done to certain angle theta, isn't it? So mb sin theta d theta, from where to where done? Theta 1 to theta 2 we have done. So work done is nothing but potential energy. Work done is nothing but we are going to get the potential energy. So mb is constant, we are going to get MB cos theta 1 minus cos theta 2 you are going to get in that way, isn't it? Okay. Now what we are going to get? Okay. So this is what? If theta 1 is equal to 90 degree means cos 90 is, okay, cos 0 is 1, isn't it? Cos 0 is 1. Okay, so 90 degree means 0, this much you are going to get. So we are going to get MB cos theta, or theta 2 is 90 degree, cos theta 1 is theta, if you take means we are going to get minus, okay, minus m dot b, we have got mb cos theta we are going to get. So negative means the work done is negative, that's what. Negative means work done is negative. That is, we should know. These are all formulas, problems we know, or formulas we know. Simply, again we are going to refresh it, we are going to return. So this is the derivation already we have discussed. Okay, so this is what. Now if a magnet is there means we are going to write down the magnetic field lines, isn't it? Magnetic field lines. So magnetic field lines are nothing but the visualizations, okay, visualization. So again we are going to talk about the magnetic field lines, how it is visualized, and what are the physics behind that, and what are the topics we can get for our competitive examination in our next classes. Okay, thank you.
Don't forget to like our video and subscribe our YouTube channel for all the updates.